So the ambient air is first decelerated in a diffuser before it enters the compressor. Approximating both the diffuser and the compressor to the isentropic determine the stagnation pressure at the compressor inlet, the required compressor work per unit mass if the stagnation pressure ratio of the compressor is H. So at the end of the day, this is still an open system analysis. So you just need to see what you have here. So an aircraft engine component, we will look at their component in more detail after this. So here we are just trying to look at the basically technical properties. So you are given on this street, there is a velocity here which is 250, so meaning this is definitely not a stagnation properties. So the stagnation properties will be different. So here we need to find out the stagnation pressure at the compressor inlet. Of course, before that we have a diffuser. Okay, let's see how we approach this. So for this particular chapter, we mostly don't use table based anymore. Meaning, for this particular chapter, just like applied fluid, we use constant specific, so Cp and K. So we just focus on the Cp and K. Because usually your temperature change won't be too high as well. So approximating that at room temperature should be quite accurate. Because if when it comes to Brayton cycle, temperature change is very high. So when you assume constant specific and error is higher, but here temperature is relatively compensating that big difference, so it's okay. Okay, so first thing you need to find the stagnation temperature and pressure. So very straightforward. You just need to use the equation just now that you see. So T01 equals to T1 plus V1 squared over 2Cp. And T01 equals to, and then from the temperature, you use the isentropic relation equation. You can find the stagnation pressure, which is what the equation has. So like in this case, right, it doesn't really matter whether the stagnation point that you are looking for is here or here. Because that thing is just a diffuser. Ultimately, stagnation point just means that the velocity is very low or zero, close to zero. So those two should have the same stagnation point, stagnation property, because the diffuser doesn't have work into output, it doesn't have any Q into output. So same thing. So when it comes to B, then different case, meaning the outlet of the compressor. Actually, B what is B? So B asks for the required compressor work per unit mass, and the pressure ratio is 8. So here you have a pressure ratio. You are given the pressure ratio. You need to find the compressor work. So this time you can use T01 for answer more explanation. So the temperature increased by 31.1 degrees Celsius compared to the original temperature. Pressure increased by 26.7. Okay, so now in order for us to find the compressor work, then again you need. So this is so what you just found, T01 is the temperature and pressure of the inlet of the compressor. So obviously you need the outlet of the compressor in order for you to find the work. So to find the temperature of the outlet, or rather to find the temperature at the outlet of the compressor, so that you can find the compressor work, you can again make use of the isentropic equation. So this is the same thing as Brayton cycle and compressor. So T01 2 over T01, so T01 is the inlet of the compressor. T02 is the outlet after the increase in the pressure. So compressor ratio is given 8. So you can submit T02 over T01. From here you get the temperature. So to find the work input is simply Cp T02 minus T01. Part A is the new one, there's a new part B is pretty much just the same cycle. Because technically speaking, the jet propulsion cycle is a bit, but a bit more complicated. first, then only you put the compressor. So actually you can see it's about the same thing. Alright, so the first part is to find the temperature properties, so then after that find the parameter. So, okay, so we cover temperature properties, so we leave it here first. Yeah, the flow is actually a kind of the same. After that we talk about speed of sound. But this time I will show you the derivation, so straight into the equation. So speed of sound equation, main thing, this is the beginning part, I skip the derivation. Ultimately, speed of sound equation is C equals to square root KRT. Same equation. So C is the speed of sound, KRT. So based on this equation, you should see that speed of sound is only affected by two things. One, temperature. So higher the temperature, the higher the speed of sound is. Second thing, KR is type of gas. Because KR is in a way constant depending on what gas you have. It's constant if you change the gas. So speed of sound will only vary based on type of gas as well as temperature. Other than that, no other properties will affect speed of sound. Okay, so you can see here also. So 200 Kelvin, air and helium has different speed of sound, 300 Kelvin, and then 1000 get different speed of sound. And if we have speed of sound, then we have Mach number. So Mach number ratio of actual speed and the fluid to the speed of sound in the same fluid at the same state. So Mach number can be different at different temperature, even if the flight speed is the same, for the same reason just now. Because if you replace this one with square root KRT, if temperature is different, then Mach number is different. So you can see here also. So yeah, then so Mach number equals to 1, you get sonic speed. Mach number higher than 1, you get supersonic. Less than 1 is subsonic. That one we will approach later on the code. So now that this is out. Okay, so the speed of sound in air increases with temperature. So at typical outside temperature, C is about 340 meters per second. Thus is about 200 Kelvin plus. So in round numbers, therefore, the sound of thunder from a lightning strike travels about 110 to 3 seconds. So if you see the lightning and then you hear the thunder in less than 3 seconds later, then it means that the lightning is actually very close. So you can count on. So within that time, yeah, because based on this lightning, the sound travels in 110 to 3 seconds. So if you hear it within 3 seconds, meaning the lightning strike is less than 110 or very far. Much better. Yeah, speaking of this, I don't know whether you guys got, because yesterday night was something, the lightning strike was very, very strong. You can see for something. Not very stupid. It feels like someone is walking my house. My house also, it started about 4 o'clock. It was very loud. My house was okay, so quick example on speed of sound in Mach number. So air enters the diffuser with a speed of 200 meters per second. Determine the speed of sound and the Mach number at the diffuser insert when the air temperature is 30 degrees Celsius. So nothing special here. So speed of sound in air at 30 degrees Celsius. C equals to square root KRT. So K 1.4, 0.0. Okay, now this one, right? It is better for you to keep the whole at it. So what I mean is this. Because when you come to thermal, right, we always convert everything to kilo. But then if you use kilo in this equation, right, then you need to times the 1000 back. Otherwise it will be a bit off because of the square root. Because of the square root. So here you need to convert to kilo. So it is better if you use like 287, right? But again, this one is up to you. So you can see here, we use like what we do in thermal. So 1.4, 287, 03, but 1000. Because this is the unit conversion for kilo. Otherwise, it will screw up the value. So then the Mach number, yeah, we can calculate the Mach number. So 200 over the speed of sound, we get the Mach number. And also calculation, always remember temperature is in Kelvin.
So I always use 287 kind of.
If you always use 287 all this while, even for other calculations, then you have to remember that your value is not in kilo.
Then it's in
normal.
Or joule.
Because thermal we always use kilo, that's why I always use 287. Just that when it comes to this chapter, then a bit more. Okay, so that's one thing that you need to be a bit careful. Okay, so we look at one-dimensional isentropic flow. Okay, so during fluid flow through many devices such as nozzle, so here we look at the nozzle, diffusers and turbine blade passages. So here this is primarily nozzle. Flow quantities vary primarily in the flow direction only, and the flow can be approximated as one-dimensional isentropic flow. Okay, so what we are doing here, or what you are shown here, is pretty much this. This entrance of the nozzle, this is more or less a converting garbage nozzle. So, and the stagnation region, these are the information. So this is CO2. So one thing you need to be careful here, this example is based on CO2. So the value might not be as for what you do. Because what you will do is add or more. So this is CO2. So slightly different. Alright, then this graph shows you how all of these variable changes depending on which location it is at through this nozzle. So through this nozzle, the pressure will definitely reduce. This one will go. Otherwise, nozzle cannot complete nozzle's way of changing the velocity through the reduction of pressure. So it definitely has high pressure here, low pressure here. So this is the area. So the area of the thing first is high, then it becomes smaller, then it increases back to here. Then this will be how the Mach number changes. This is how the velocity changes. The red line is the temperature and the purple line is the density. So this is just a graphical representation. Of course, we need some values just to see this line. So this is the variation of the normalized fluid properties and cross-sectional area along the time as the pressure drops. So as the pressure drops, this is how the graph looks like. Okay, so we use this as an example for calculation. So carbon dioxide flows steadily through a very cross-sectional area duct at a mass flow rate of 3 kg per second. So just like everything in thermal, this doesn't change. Mass flow is always constant throughout the whole thing. The carbon dioxide enters the duct at a pressure of 1400 kPa and 200 degrees Celsius with a low velocity. So these are the stagnation properties. 1400 kPa, 200 degrees Celsius. And it expands in the nozzle to an exit pressure of 200 kPa. So here 1400 and exit 200. Assume isentropic flow. Determine the density, velocity, flow area, and Mach number at each location along the duct that corresponds to an overall pressure drop of 200 kPa. Meaning, we are asking you to find each of these values for every 200 kPa. Technically, this is what you do for, like, let's say, experiment. Right? So that's how you get all those graphs at the start. Of course, I'm not going to ask you to do this here unless you are interested. So here we will show you one example. Looking for, I think, one more points, and then you will be provided with the table of the answer here. Okay, so we will see how we can find for one of them. Of course, for every precision location, the method is the same. So, as usual, our assumption, so here we assume carbon dioxide is also an ideal level of specificity at room temperature. And the flow through the duct is steady, one-dimensional, isentropic, and so steady flow. The steady flow something is still observable, so that you can say mass flow is a constant. compressor. So for carbon dioxide, the Cp value, K value, and R value are as follows. Again, you can get from the table. But this is carbon dioxide. Okay, so we want to find everything here. Density, velocity, flow, area, mass number. Okay, so first thing, we usually just find temperature. So we establish this first. So we know that T naught is 200 degrees Celsius. So 473. P naught is 1400 kilopascal. So we look for the first location. So the first location is at 1200 because we want to find for step size of 200. So we look for 1200 first. So to illustrate the solution procedure, we calculate the result properties at 1200 kilopascal. So same thing, isentropic equation. So T over term, that's why the isentropic solution is important. Because we are doing the isentropic equation here. So T over T naught equals to P over P naught, K minus 1 okay. So from here you get the temperature. So the temperature at 1200 kilopascal is 457 Kelvin. And then velocity. This one we short form this equation. But basically this is this equation. This one where to do this, so let's is actually this equation. Okay, so you move this. So V squared equals to 2Cp T naught minus T. So V equals to square root 2Cp T naught minus T. So this is the equation that we are using. Find that particular change there. So here we also have the same issue as when we use as we find the speed of sound. Meaning the Cp here is also in terms of thousand. Kilo. So you need to convert it to thousand. So you can see in the solution there as well. So in this solution, so same equation, 2Cp T naught minus T. So 0.846, because this is kilojoule, right? So ultimately we multiply by 1000. So same thing as for the speed of sound just now. Because of the square root, otherwise then the value will be very long. So times this one, then you can get the velocity. So basically you represent at this 1200 kilopascal, temperature is that, velocity is this. Of course we are not done looking for everything yet. So we still need to find density. Density you can still use the isentropic relation if you want to, but we do also have a simpler way. You can just use the ideal relation. So density equals to P over RT, then you can get density. P equals to MRT, so P RT, so P equals to RT over density. So PV equals to MRT. So P equals to RT over density. So you move them around, then you get this. Sorry, the other way around, right? Okay. V over M, yeah. V. So density you can find through angular relation. Then area. So area primarily we make use of mass flow rate. So rho AB. So this is pretty much the only equation that you have that is based on the area. So you can use mass equals to rho AB, mass flow rate equals to rho AB, and from here you can get the area of the at that point, and then. Yeah, then speed of sound, C equals to KRT, and then ultimately Mach number. So let's say if you repeat all of these calculations for each of them, so this will be what you see. So like in this graph, it shows you what are the values for each of the point. But of course, we still got one point here. We put an asterisk at 767 kilowatt hour, and it says that this is the critical pressure where the local Mach number is 50. What is this one? It is the point where you get. So let me and you get the name of it. Critical is the property thing. What kind of flow are you looking at? There's the name one. You haven't knew one. What is the location called? No. Sanitation, the whole thing is sanitation. Throughout the whole nozzle is sanitation. What happens if you get something stuck on the throat? That makes you want to and you get and it comes to flow. Okay, so from the example, we know that the flow area decreases with decreasing pressure down to a critical pressure value where the Mach number is 80. So at that point, we call the area throat. And the velocity of the fluid keeps increasing after passing the throat, although the flow area increases because we had a choke flow over there. But this one later when we study about convergent diverging motor, we will come back to it. So this increase in velocity past the throat is due to the rapid increase in the fluid density. So the flow area of the duct first decreases and then increases. Such ducts are called converging diverging nozzle. So there's also one thing called venturi nozzle that looks the same, but that one is not actually a converging diverging nozzle because we will explain that is for compressible flow. Okay. So yeah, the area is called throat. Okay, and if you get one number equals to 1 at that point, then it means you get a throat. Because at that point you cannot go higher, that's why it's called throat. Okay, so now we will do a quick derivation on how the fluid velocity change with flow area. So let's say if we have a conservation of so H1 plus D1 square over 2 is H2 plus D2 square over 2. And so we say this thing is constant. Actually, we're going to do that. So if we differentiate this equation, we get dH plus d dV. And also, we take the second law equation. dds equals to dH minus dV. This is the equation in the second law. Most likely, none of you remember this. This from the entropy factor. Okay. But actually, nothing. It is just Q minus W equals to delta hypercalculate. Then you move around so you get TDS equals to dH minus dV. So we are talking about isentropic flow here. So we say dH equals to VdP equals to 1 over rho dV. And we sub this back into the equation, you get this relation. So dP over rho plus dV equals to rho. So what is the point of this? So we sub again. So now at the bottom here, you can see we submit a nice flow equation. So we use the differential form of the flow equation. You get this. So this is what do you call this? Derivation by what derivation is? There's a name. By the way, partial differentiation. So you get that equation. So when you combine these two, right, what you get is this equation. Alright, but what is the significance of this equation? This equation basically represents how pressure, velocity, and mass will change based on the area of the pump. And this is the equation that we use to prove that if you have a converging diverging nozzle, if you have a converging nozzle, Mach number is less than 1, the Mach number less than 1, Mach number is 1. Okay, so let's look at this. So this relation describes the variation of pressure with flow area. Okay, so for subsonic flow, the normal flow that we deal with, Mach number less than 1. You can see that. So if your Mach number is more than 1, it's less than 1, this value is positive if as pressure increases. So the pressure So the pressure decreases in converging ducts and increases in diverging ducts. So it means that if this increase, this will increase. And if this reduce, then this will reduce. If Mach number is less than 1. Okay, so again, so let's say in subsonic flow, this term is always positive. So area is proportional to pressure. So as area reduces, pressure will reduce. As area increase, pressure will increase. If you have supersonic flow, so supersonic flow, then the other way, this is the other way around. This 1 minus temperature is negative, so then they are the other way around. So this is also the whole reason why you cannot achieve supersonic flow if you only have convergent nozzle. Because after that it will become a diameter basically. So the carry forward. So now this equation, if you replace the P with V, based on that equation, if you replace the P with V, then it becomes a bit more obvious. So now you look at this. So this equation governs the shape of a nozzle or diffuser in subsonic or supersonic isotropic flow. So same thing. If you have a Mach number less than 1, you have Mach number less than 1 subsonic flow, then once again this thing is positive. So you can see that as area reduces, velocity will increase. So that's why this is a nozzle. But so this is the nozzle, the velocity will increase. And if you have a supersonic flow, then this becomes negative, then the case becomes the other way around. Then a converging nozzle will become a diffuser instead. Because the relationship will swap. So then for sonic flow, then yeah, it's just 0. The sonic flow is just 1 over that. So you cannot attain supersonic velocity by extending the converging section of a converging nozzle. So doing so will only move the sonic cross section further downstream and increase the mass flow rate. So if you keep increasing the converging nozzle, you are just moving the choke area. You will not be increasing the velocity further. The highest that you can reach is sonic flow. So to accelerate a fluid, we must use a converging nozzle at subsonic velocity and a diverging nozzle at supersonic velocity. To accelerate a fluid to supersonic velocity, then we need to use a diverging nozzle. Okay, so yeah, here is just one quick example here. Yeah, we'll also stop here. So subsonic flow. If you have subsonic flow, then this shape will give you a nozzle. This shape is a diffuser, standard thing that you know. But if you have a supersonic flow, then it's the other way around. So this is actually a nozzle. The part that is actually the diffuser. So we also have a summary of how each of the properties change downstream, basically. So you can see here, we go downstream, pressure decrease, enhance velocity increase. Velocity increases So of course, for the whole equation to make sense, this one thing you need to remember lah. This equation makes sense because area and velocity is always positive value, not negative value. The negative value is always equal to the other way around, so that's not what it is. So we always assume they are always a positive value, so that's why we get this kind of relation. Alright, so we'll stop here. Tomorrow we will continue later next week. As the best is. So next week we will continue. Then yeah. Hopefully next week. Everything. No lecture